At the end of this video, you should be able to state the kinetic molecular theory of matter and describe how it explains certain properties of matter. List the 5 assumptions of the kinetic molecular theory of gases and define the terms ideal gas and real gas. Describe each of the following characteristic properties of gases: expansion, density, fluidity, compressibility, diffusion, and effusion, as well as describe the conditions under which a real gas deviates from ideal behavior. In the unit Matter and Change, you learned that matter exists on Earth in the forms of solids, liquids, and gases. Although it is not usually possible to observe individual particles directly, scientists have studied large groups of these particles as they occur in solids, liquids, and gases. In the late 19th century, scientists developed the kinetic-molecular theory of matter to account for the behavior of the atoms and molecules that make up matter. The kinetic-molecular theory is based on the idea that particles of matter are always in motion. The theory can be used to explain the properties of solids, liquids, and gases in terms of the energy of particles and the forces that act between them. In this section, you will study the theory as it applies to gas molecules. First main idea. The kinetic molecular theory explains the constant motion of gas particles. The kinetic molecular theory can help you understand the behavior of gas molecules and the physical properties of gases. The theory provides a model of what is called an ideal gas. An ideal gas is a hypothetical gas that perfectly fits all the assumptions of the kinetic molecular theory. The kinetic molecular theory of gases is based on the following 5 assumptions. 1. Gases consist of large numbers of tiny particles that are far apart relative to their size. These particles, usually molecules or atoms, typically occupy a volume that is about 1,000 times greater than the volume occupied by an equal number of particles in the liquid or solid state. Thus, molecules of gases are much farther apart than molecules of liquids or solids. Most of the volume occupied by a gas is empty space, which is the reason that gases have a lower density than liquids or solids do. This also explains the fact that gases are easily compressed. 2. Collisions between gas particles and between particles and the container walls are elastic collisions. An elastic collision is one in which there is no net loss of total kinetic energy. Kinetic energy is transferred between 2 particles during collisions. However, the total kinetic energy of the 2 particles remains the same, as long as temperature is constant. 3. Gas particles are in constant, rapid, random motion. They therefore possess kinetic energy, which is the energy of motion. Gas particles move in all directions. The kinetic energy of the particles overcomes the attractive forces between them, except near the temperature at which the gas condenses and becomes a liquid. 4. There are no forces of attraction between gas particles. You can think of ideal gas molecules as behaving like small billiard balls. When they collide, they do not stick together, but immediately bounce apart. 5. The temperature of a gas depends on the average kinetic energy of the particles of the gas. The kinetic energy of any moving object, including a particle, is given by the equation at the bottom of your screen now. In this equation, m is the mass of the particle, and v is its speed or velocity. Because all of the particles of a specific gas have the same mass, their kinetic energies depend only on their speeds. The average speeds and kinetic energies of gas particles increase with an increase in temperature and decrease with a decrease in temperature. All gases at the same temperature have the same average kinetic energy. Therefore, at the same temperature, lighter gas particles, such as hydrogen molecules, have higher average speeds than do heavier gas particles, such as oxygen molecules.
The kinetic-molecular theory describes the behavior of gas molecules and the physical properties of gases. The kinetic-molecular theory views gases as being made up of large numbers of fast-moving particles that are far apart from each other. Most of the volume occupied by a gas is empty space. Gas particles are in continuous rapid random motion, and the forces of attraction or repulsion between them are essentially non-existent. Kinetic molecular theory relates the kinetic energy of gas particles to the temperature of the gas. Gases differ from solids and liquids in that they expand to fill the shape of their container. Because there are large distances between gas molecules, gases have extremely low densities. Carbon dioxide, for example, is less dense than water, so bubbles of carbon dioxide rise to the surface. Gases are compressible to small fractions of their initial volumes. Because of this, large amounts of oxygen can be stored in tanks for scuba diving. Gases mix readily by diffusion. We don't have to stir or shake them to make them mix. Gases can escape containers through tiny holes in a process called effusion. This occurs when a bicycle tire is punctured.
Second main idea. The kinetic molecular theory explains the physical properties of gases. The kinetic molecular theory applies only to ideal gases. Although ideal gases do not actually exist, many gases behave nearly ideally if pressure is not very high and temperature is not very low. As you will see, the kinetic molecular theory accounts for the physical properties of gases. For example, expansion. Gases do not have a definite shape or volume. They completely fill any container in which they are enclosed and take its shape. A gas transferred from a 1-liter vessel to a 2-liter vessel will expand to fill the larger volume. The kinetic molecular theory explains these facts. According to the theory, gas particles move rapidly in all directions, see assumption 3, with no significant attraction between them, see assumption 4. Fluidity. Because the attractive forces between gas particles are insignificant, again see assumption 4, gas particles glide easily past one another. This ability to flow causes gases to behave as liquids do. Because liquids and gases flow, they are both referred to as fluids. Low density. The density of a gaseous substance at atmospheric pressure is about 1/1000th the density of the same substance in the liquid or solid state. The reason is that the particles are so much farther apart in the gaseous state. See assumption 1. Compressibility. During compression, the gas particles, which are initially very far apart, again see assumption 1, are crowded closer together. The volume of a given sample of a gas can be greatly decreased. Steel cylinders containing gases under pressure are widely used in industry. When they are full, such cylinders may contain more than 100 times as many particles of gas as non-pressurized containers of the same size could contain. Diffusion and effusion. Gases spread out and mix with one another, even without being stirred. If the stopper is removed from a container of ammonia in a room, ammonia gas will mix uniformly with the air and spread throughout the room. The random and continuous motion of the ammonia molecules, again see assumption 3, carries them throughout the available space. Such spontaneous mixing of the particles of two substances caused by their random motion is called diffusion. Gases diffuse readily into one another and mix together due to the rapid motion of the molecules and the empty space between the molecules. The gas molecules in each of the two flasks that are shown on the screen here continuously move about in separate flasks because the stopcock is closed. When the stopcock is open, the gas molecules continuously diffuse back and forth from one flask to the other through the opening. Diffusion is a process by which particles of gas spread out spontaneously and mix with other gases. In contrast, effusion is a process by which gas particles pass through a tiny opening into a vacuum. The rates of effusion of different gases are directly proportional to the velocities of their particles. Because of this proportionality, molecules of low mass effuse faster than molecules of high mass.
Diffusion is the random mixing that occurs when two gases come into contact with each other. The random motion of gas particles causes the gases to mix. When the stopcock is opened, the lighter hydrogen molecules diffuse faster than heavier nitrogen and oxygen particles in air. Given enough time, the flasks will have exactly the same composition. Effusion is different from diffusion. When a gas effuses, it passes through a small hole in its container, being pushed by the pressure of the container. When this balloon ruptures, it contracts and pushes the air out of the balloon.
Third main idea. Real gases do not behave according to the kinetic-molecular theory. Because particles of gas occupy space and exert attractive forces on each other, all real gases deviate to some degree from ideal gas behavior. A real gas is a gas that does not behave completely according to the assumptions of the kinetic-molecular theory. At very high pressures and low temperatures, the gas particles will be closer together, and their kinetic energy will be insufficient to completely overcome the attractive forces. At such conditions, the gas deviates from ideal behavior. At very low temperatures or very high pressures, gases condense to the liquid phase. The figure on your screen here shows what happens to a gas in a car's engine cylinder as the pressure is increased. Increase the pressure sufficiently, and the gas will begin to deviate from ideal behavior. The kinetic-molecular theory is more likely to hold true for gases whose particles have little attraction for each other. The noble gases, such as helium and neon, show essentially ideal gas behavior over a wide range of temperatures and pressures. The particles of these gases are monatomic and thus nonpolar. The particles of gases such as nitrogen, N2, hydrogen, H2, are nonpolar diatomic molecules. The behavior of these gases most closely approximates that of the ideal gas under certain conditions. The more polar the molecules are, the greater the attractive forces between them, and the more the gas will deviate from ideal gas behavior. For example, highly polar gases such as ammonia, which is NH3, and water vapor, which is H2O, deviate from ideal behavior due to a larger degree than do nonpolar gases. At this point, you should be able to state the kinetic-molecular theory of matter and describe how it explains certain properties of matter. List the 5 assumptions of the kinetic-molecular theory of gases. Define the terms ideal gas and real gas. Describe each of the following characteristic properties of gases: expansion, density, fluidity, compressibility, diffusion, and effusion. And lastly, describe the conditions under which a real gas deviates from ideal behavior.